Good day to our lecturers and fellow peers. Today, Kishendran and I will be presenting our instrumentation project, which is a smoke detection system using an Arduino UNO and the MQ2 gas sensor. Our goal was to build a reliable safety system that uses a dual level alert protocol to accurately detect smoke in real time. For this presentation, we are focusing specifically on section A, which covers transducers. We will deep dive into why we chose the MQ2 sensor, how it is classified based on our syllabus, and the exact chemical physics that allow it to see smoke in the air. Meet the MQ2 sensor. To start, the MQ2 is the heart of our system. We chose this specific transducer because it is highly sensitive to a wide range of combustible gases and smoke. In terms of engineering design, it is a chemoresistor. This means its internal electric properties change based on the chemical environment surrounding it. It is an incredible popular choice for instrumentation because of its rugged build and its ability to provide a continuous analog signal that an Arduino can process instantly. Okay, transducer classification 1. Based on the classification method we learned in week 1 to week 6, we have identified several key types for the MQ2. First, it is a resistive transducer. Its primary method of sensing is changing its internal resistance. Second, it is a passive transducer. It does not generate its own electricity like a solar cell would. Instead, it requires a steady 5-volt DC supply from the Arduino to power its internal heater and sensing circuit. Finally, it is an analog transducer. The output is a continuous voltage signal, not just a simple on or off pulse. Continuing with our classifications, the MQ2 is a contact transducer. Unlike a motion sensor that works from a distance, the smoke particles must physically enter the sensor chamber to be detected. It is also an input transducer, as it takes a physical environmental quantity and converts it into electrical data. One of its best characteristics is that it is a fast response sensor. Once the internal element is warmed up, it can detect a spike in smoke level within milliseconds, which is critical for life-saving application. Now let's look at the actual material inside the sensor. The active sensing layer is made of tin dioxide or SnO2. This is an N-type metal oxide semiconductor. As you can see in the molecular representation on the slide, this material is specifically chosen because its conductivity is highly dependent on the oxygen molecule present on its surface. This is the brain of the transducer that makes the whole project possible.
Okay, this is the most important part of our project, the chemoresistive effect. In clean air, the internal heater warms the thin dioxide layer, causing oxygen to stick to its surfaces. These oxygen molecules trap electrons inside the material, which creates a very high electrical resistance. However, when the smoke enters the sensor, the gases react with the trapped oxygen and release the electrons back into the semiconductor. This causes the resistance to drop instantly. This physical change in resistance is what the Arduino actually measures. To turn that change in resistance into something that Arduino can read, we have implemented a voltage divider circuit. Since the MQ2 is a passive resistor transducer, we place it in series with a load resistor. As smoke makes the sensor resistance drop, the current in the circuit increases. This results in high voltage being dropped across the load resistor, which is then sent to the AO analog pin. We have verified this entire logic using the Tinkercad simulation you see on the screen. We will put the Tinkercad simulation at the end of this video. Our code uses this analog data to create two levels of safety at a reading of 500, which represents the moderate smoke level. The Arduino triggers a red light on pin 4 as a visual warning. If the situation escalates and the readings hit 650, the system triggers the piezo buzzer on pin 7 to sound a loud alarm at 523 Hz. This shows how we can take a raw transducer data and turn it into a functioning safety instrument. So we completed this project over a strict 2-week timeline. Week 1 was dedicated to the technical research of SN02, material and specification, which I handled. I focused on formulating the chemoresistive principle and building the Tinkercad schematic. In week 2, we worked together to record this presentation and finalize the report to meet all the lecturers' requirements. Thank you, ma'am, and we will attach our Tinkercad simulation at the end of this. Simulation for our Tinkercad. Firstly, when we start the simulation, there is a smoke here, and you can see the serial monitor, which is when there is no smoke, it doesn't increase. But when we bring this smoke close to the smoke sensor, this LED will light up, and this buzzer will produce sound, which is what we will be hearing. And you can see the serial monitor increasing when we go down. Thank you.